Greetings to all the viewers. The session is going to deal with target CSIR NET JRF coming examination and also state eligibility for teaching and so many competitive exams pertaining with the government examinations as well. Whatever the concept it might be, the standard chemistry questions are taken over there. Previous year question paper, CSIR NET 2025 solved previous year question paper is available. And we already conducted series of sessions which are available Dr. Kavitha Chemistry Academy channel. Earlier it will be World of Competitive Chemistry, right? So you can subscribe the channel Dr. Kavitha Chemistry Academy so that you will get the sound information regarding the competitive examination chemistry, research oriented chemistry, and also about the competitive examination chemistry. Here in continuation to earlier session, so here 2025 June CSIR NET chemical science question paper is going to be discussed. So here question number 36 is going to taken into the consideration, being it is a part B question, so 2 marker question it will be. So there will be a negative marking if you are mentioning wrong answer. 0.5 negative means marks will be deducted from your total score. Let me introduce the question. A compound A on Hoffman exhaustive N-methylation procedure involving 2 cycles followed by ozonolysis using O3 and dimethyl sulfide gives benzaldehyde, formaldehyde, 2,2 dimethyl propane diol. The structure of A could be, here 4 different options are provided. If you observe clearly, all are piperidine skeletons only, and there will be a 2 methyl groups, 1 phenyl group is there at different positions. We need to identify how the Hoffman exhaustive and methylation and followed by ozonolysis giving rise to one of the correct answer among these 4, right? In order to get that one, first of all, starting compound is cyclic secondary amine. All are piperidine skeletons only, so that it is a secondary amine. 2 Hoffman elimination cycles open the ring generating diene, right? So here when Hoffman exhaustive N-methylation procedure operated on these nitrogens, so that N-methyl. So here quaternary nitronium will be generated, that will be discarded, and the directly connected carbons will be transformed into a double bonded carbon atom. Then you can find at the terminal carbons there is a double bond. Benzene ring attached to the carbon adjacent to the nitrogen. Geminal dimethyl groups carbon opposite are appropriately positioned at the ring system. Sufficient beta hydrogens to get the Hoffman elimination process. Being the adjacent hydrogen to be removed. That's the reason why beta hydrogens are essential for Hoffman elimination process, right? Here is the clear description regarding that Hoffman elimination process. If you are taking the starting material, we are going with the compound number 1, whichever provided in the option number A. So where you can find a piperidine ring with the phenyl at the position number 2 and the 2 methyl are located at the position number 4. That is supposed to be added with methyl iodide. Hoffman exhaustive methylation is supposed to be treated with the alkyl iodide. Methyl iodide is treated over there, so that N-methylation taken place. Further methylation taken, being it is the 2 equivalent reaction is required, being it is a secondary amine. That's the reason why N, N dimethyl derivative got generated, which is designated as a quaternary ammonium salt. Whichever generated over here is called quaternary ammonium salt. Quaternary ammonium salt is supposed to be treated with the silver hydroxide. Here is the Hoffman exhaustive methylation taken, so that the bond between the carbon and nitrogen broken and the bonded electrons taken with the nitrogen atom, and here is the opening of the ring taken place like this, and the nitrogen is becoming a tertiary one, and with respect to this nitrogen, the adjacent carbon is called alpha and the next position is beta. Beta hydrogen is discarded and giving rise to double bond in between, so that you can achieve a double bond in between the carbon and carbon atom. Wherever the bond broken, cyclic ring got broken between the carbon and nitrogen, that is experiencing olefinic double bond nature. Later on, Again, you can go for the methylation by adding with methyl iodide one more time, so that again quaternization got carried out. Whenever quaternization got carried, again the cleavage taken, exhaustive methylation, so that your heating required in the presence of silver hydroxide, so that your bonded electrons are taken with the nitrogen atom over this heterolytic cleavage pathway, so that your nitrogen is discarded as a trimethylamine, and here the beta hydrogen is very essential for Halfman exhaustive methylation process, so that here the double bond generation in between and beta hydrogen is eliminated, and here you can experience one more double bond in between. So here the double bonds whichever located over there are called isolated. They are not exactly in the conjugation. Both the double bonds are isolated double bonds, and they are present on the two terminal carbon atom, and this is said to be 1,4-diene. First, second, third, fourth, first and fourth carbons are having double bond nature. That's the reason why 1,4-diene got originated by Halfman exhaustive methylation process. This is the step number 1. Later, we need to go for ozonolysis products, ozone treatment. Whenever ozone is added, simply you can break the double bond in between, and the carbons are directly connected with the double bond got converted into their corresponding carbonyl functionalities. Wherever you can find PH-CH double bond, if you are breaking this double bond so that it is transformed into a kind of aldehyde functionality subsequently, benzaldehyde is the product. And this is the carbon becoming aldehyde once again, and here is the CH4 functionality, here CH2 remains as such. So ozonolysis is more specific for the cleavage of double bonds only, so that here one more double bond got cleaved by means of ozone treatment. Here is the another aldehyde functionality got originated with the 3 carbon atom skeleton, and another fragment you noticed over there, that is becoming a formaldehyde. Let me show the entire picture for that kind of cleavage. Whenever this is the case, subjected to ozonolysis, specific for the double bond cleavage, only double bond completely broken, and the carbons directly linked got converted into corresponding carbonylic functionalities. Here the carbon is attached to the benzene ring, so that you can notice the benzaldehyde as one of the fragment over there. And this is the carbon becoming aldehyde, and this is the carbon becoming aldehyde, so that here a single compound with the 2 carbon atoms aldehydes got generated. That is a dimethyl propanaldehyde. And one more small tiny fragment you can notice at this terminal carbon atom, that is only 1 carbon of length, which is a formaldehyde. This is the entire ozonolysis procedure. Simply you need to break the double bonds for this ozonolysis process, and the carbons to aldehydes or ketones. So if we are getting all these kind of products in the similar manner, whichever mentioned within the problem, they mentioned benzaldehyde, we got the benzaldehyde. One another is a dimethyl propanediol, that is also we got it. So another is a formaldehyde. So all are possible if we are taking starting material as option number 1. Option number 1 is providing all the requisite products whichever generated by Halfman exhaustive and methylation, followed by ozonolysis process. For question number 36, option 1 could be the right answer. Let me go with this is the correct answer. So option 1 could be the right answer. Let me go with question number 37. The correct order of basicity for the following compound is, if you are taking 3 different compounds, all are made up of 6-member ring system, all are made up of 2 nitrogen atoms, all are made up of aromatic rings. Only the difference is position of nitrogen atoms. If 2 nitrogens are oriented at the 1, 2 positions, 1, 3 positions, 1, 4 position, what kind of order of basicity you can notice? How can we arrange all these compounds in accordance with the increasing order of basicity, right? In order to get that one, we have options here. First one is called pyrazine at 1, 4 position diazine. So the second one is called pyrimidine, that is 1,3-diazine, and pyridazine. Another is a pyridazine. There is a difference between pyrazine and pyridazine. Pyrazine means 1,4-diazine, pyrimidine is 1,3-diazine, pyridazine is 1,2-diazine. If these three compounds are distinguished by the position of the nitrogen atoms, here the very essential thing is diazine approximate pKa values are provided. Pyridazine, first compound is called pyridazine. Pyridazine is the 1,2-diazine whose pKa value is provided as 2.3. Pyrimidine is 1.2. Pyrazine value is provided as 0.6. Higher pKa value conjugate acid means stronger the base it will be. So that pyridazine is having higher pKa value, that indicates it will be the stronger base. So that is provided in the option number 3. Option 3 will be higher the basicity, and followed by pyrimidine, and the next is about pyrazine. That purely depends upon the position of the nitrogen atom favored for the higher electron density of lone pair of electrons. Higher electron density of lone pair of electrons having more provision to release the electrons, having higher the basic nature. Greater the electron density, greater the provision to release the electrons, greater the basicity of the compound. That is given in the option number 3. Later on, these two nitrogens are far apart. Both are separated by one carbon atom, so that electron density got separated slight extent. If you go with the option number 1, where you can notice the electron densities are far away in comparison to 3 and 2. That's the reason why here the basicity is still lowered. Here, option 3 followed by 2 followed by 1, that is given in the option number 4. For question number 37, option 4 could be the right answer. Option 4 could be the right answer. 3, 2, 1. So simply 1,2-diaza higher basicity, 1,3-diaza, 1,4-diaza basicity gradually decreases, right? Let me go for the next question, question number 38. Isoquinoline on sequential reaction with benzoyl chloride and potassium nitrile, followed by heating with the aqueous sodium hydroxide gives. This is the named reaction. So in order to get the proper product of this isoquinoline, this is a part of heterocyclic chemistry, again organic chemistry question it will be. So here, let me introduce the named reaction over there. Isoquinoline upon reacting with benzoyl chloride, obviously there is a nitrogen, so that in benzoylation taken, so that in benzoyl isoquinoline salt formation taken place. Whenever potassium nitrile is added over the salt, your result reaction, this is the named reaction just now we discussed, result reaction taken place, and aqueous sodium hydroxide that able to remove this N benzoyl group, and subsequently you can achieve that compound number 1. Compound number 1 is provided, that is here. So 1-cyano isoquinoline could be the correct answer. Let me show how it is possible. Isoquinoline, benzoyl chloride if added, and benzoyl isoquinolinium chloride, such a salt formation taken place. Further nitrile group, nitrile is the nucleophile, so that here the attacks, whenever potassium nitrile is added, C1 carbon is having the more provision to get such kind of result reaction. Nitrile group go specifically toward the carbon number 1, so that cyano substitution taken at the first position, 1-cyano got generated. Later on, aqueous sodium hydroxide if added, benzoyl group got removed. So here the removal of benzoyl group taken, and we got finally 1-cyano isoquinoline as a final product. In order to get this reaction, there is a schematic representation provided. First of all, I am taking isoquinoline as a starting material. Benzoyl chloride is added, that is capping this nitrogen, so that N-benzoyl derivative, we got it. Potassium nitrile if added, nitrile is more specific result reaction taken. Here you can observe result reaction that is taken at the position number 1, so that nitrile substituted at first carbon. Aqueous sodium hydroxide if added over this compound, here benzoyl group is specifically hydrolyzed, and here you got the free isoquinoline nitrogen atom. Isoquinoline 1-carbonitrile is the final product. Option 1 will be the right answer for this question. Option 1, we having nitrile at the position 1, and free isoquinoline is there, that is given in the option number 1. For question number 38, option 1 will be the right answer. Let me go with question number 39. The correct order of the stability of the following conformations of the propanol is. Here propanol is provided in all the options, only the difference is methyl group got shifted. Methyl group is present. Here wedge bond, dotted line bond. What does it mean? Wedge bond indicates that methyl group towards the viewer, and a dotted line bond, if methyl group is there, that is away from the viewer. If methyl group is present on the normal bond line, that indicates on the plane. So the correct stability order of the conformations to be depicted. In the first one, here methyl on the plane, and the second one, methyl indicated with the wedge bond, but that is intermediate in between. Here the methyl group wedge bond, that is indicated in the C toward the viewer. If this is the case, what could be the right stability order we need to understand? First of all, there is a repulsive forces operated between the bulky groups. What are the bulky groups? One bigger group is the carbonyl. Another bigger group is the CH3. So within the compound, we have two bigger groups. One is the carbonylic carbon. Another is the methyl functionality over this carbon atom. The perfect stability is attained whenever methyl and carbonylic oxygen are far away to each other. Whenever both are far away to each other, then the steric repulsions got minimized and they will experience higher stability. That is the fundamental operated between the stability of the conformers. Okay, so if you are considering conformation of A, methyl group is oriented most favorably away from that carbonylic functionality. Both are far apart. This location is not exactly in the same, rather both are far apart to each other. Whenever you are taking option B, there is a intermediate distance between the carbonylic oxygen and methyl. Whenever option C was taken, this methyl and carbonyl are inclined in the same direction and the distance is very less and more steric repulsions are operated. That's the reason why A is of higher stability, followed by B, followed by C. That is provided in the option number 2. Option number 2, exactly the order whatever mentioned, A, B, C having decreasing order of the stability of the conformations. If the distance is far apart, what happened? The stability got increased. That is given in the option A. Intermediate distance, intermediate repulsions, intermediate stability, option B. Shorter the distance, greater the repulsions, least the stability, option C. That is given in the option number 2. For question number 39, option 2 could be the right answer. Let me go with the question number 40. Again, it is a part of organic chemistry and we may deal with aromaticity of the given organic compounds. The major product formed in the following reaction is, we are taking only 4-member ring system with one of the double bond, and here the carbon linked with the chlorine methyl, this carbon also occupied by the chlorine methyl, and this carbon methyl, this carbon methyl. Dichlorotetramethyl cyclobutene is the name of the compound taken, added with strontium pentafluoride of 2 equivalent. This is a super acid, we can denote strontium pentafluoride. Sulfur dioxide working like a solvent media, and extremely low temperature operated -78 degrees centigrade. At this condition, after the reaction with this reagent, nature of the compound, either aromatic, non-aromatic, anti-aromatic, homoaromatic, we need to depict. For that purpose, we have here dichlorotetramethyl cyclobutene as a starting material. Reagents applied are strontium pentafluoride 2 equivalents and sulfur dioxide -78 degrees centigrade temperature is operated. Important point is strontium pentafluoride extremely stronger acid, and chloride is departed from the system, and there is a provision for the formation of carbocation intermediate. Being the compound is accompanied by 2 chlorofunctionalities, obviously there will be a dicarbocation formation taking place. Let me show that compound. So here the whenever chloride is departed from the system, carbocation is originated. So ultimately 2 two equivalents of strontium pentafluoride remove two chlorides, and there is a formation of a carbocation at the position number 1 and position number 4 as well. So here it is said to be butene dicarbocation. Butene dicarbocation will be originated. Okay, so here the resulting dication is a 4-member ring system with the 2 pi electrons. Hockel rule is applied over there. 4n plus 2 is equal to 2 electrons are located. 4n plus 2 is equal to 2, therefore n is equal to 0. N is equal to 0, it is indicated as an aromatic compound, right? So it's a very simple. Cyclobutadiene dication is a 2 pi electron system and is designated as an aromatic one. While cyclobutadiene without any charges is the 4 pi electron system anti-aromatic compound. Here we have a cyclobutene dicarbocation. It is the aromatic in nature. That aromatic compound which is satisfying the Hockel formula, 4n plus 2 pi electron system is located within, so that it is the aromatic compound. Option 1 is the correct answer. C4H4 is the anti-aromatic. C4H4 plus 2 will be the aromatic compound. So here is the very important. First of all, we need to understand strontium pentafluoride is meant for the removal of chlorides from the system, so that carbocations will be originated. So here cyclobutene dicarbocation is aromatic in nature in accordance with the Hockel pi electron system, right? So for question number 40, option 1 will be the right answer. Let me go with the question number 41. Again, it is a part of organic spectroscopy. In proton NMR, the multiplicity pattern expected for highlighted protons in the following compounds is, right? Here, the proton NMR, HNMR spectrum is provided, and these 3 compounds, protons are labeled, protons are highlighted. For these protons, how the spectral signals are, multiplicity patterns are located, we need to identify. Whenever compound 1 was considered, adjacent carbon. This adjacent carbon, no hydrogen, so that no question for proton NMR spectra. Only this side we have 2 hydrogens. 2 hydrogens located on alpha position are not exactly equivalent. One hydrogen is splitting this hydrogen as a doublet. Another hydrogen also splitting as a doublet. So the doublet of doublet, you got it. So for this hydrogen, 2 adjacent hydrogens are non-equivalent in nature. That's the reason why we got doublet of doublet. If you go with the second compound is having vinylic hydrogen atom. This vinylic hydrogen atom having this adjacent hydrogen, and here the terminal 2 hydrogens are located. Whenever this hydrogen was taken, only one hydrogen provision we have, that hydrogen will split this hydrogen by doublet. So n plus 1 multiplicity, so that here doublet is possible. And here 2 hydrogens whichever present in the terminal carbon atom, vinylic carbon atom, are not exactly equivalent. 2 hydrogens having 2 individual nature. One hydrogen is responsible for doublet, another hydrogen for doublet as well. So that here is the hydrogen doublet, here is the hydrogen doublet, here is the hydrogen doublet. Total 3 doublets are possible for the compound number 2. So here compound 2, doublet, doublet, doublet. So 3 doublets are possible. Let me go with compound number 3, where you can notice acetylenic triple bond, and here is the CH2, here is the CH2, here is the O-acetyl functionality. So labeled hydrogens, that means highlighted hydrogens, how many multiplicity patterns are there, we need to notice. For these 2 hydrogens, here is the possible next position. 2 hydrogens are located. 2 hydrogens are exactly equivalent, and n plus 1 formula is giving rise to triplet. There is a provision for a triplet. And here is the terminal hydrogen in the acetylenic carbon atom. That hydrogen is having the doublet again. So here doublet is noticed, triplet and doublet is the right answer. So that is provided in the option number 1. Let me check it. Here compound 1. Compound 1 is considered, adjacent carbon is having 2 hydrogen atom AB, both are not AA. So we can indicate as a 2 non-equivalent hydrogen atoms. One is corresponding to doublet multiplicity, another hydrogen also doublet. So the doublet of doublet is the provision for compound number 1. Let me go with the compound number 2. Compound number 2 is having, this is the hydrogen for which multiplicity to be calculated. For this carbon atom, adjacent carbon atom having only one hydrogen, that giving doublet. And here the two terminal hydrogens, both are different, so that one hydrogen is giving doublet, another hydrogen also giving doublet. So the doublet, doublet, doublet. So three possible doublets are there for this compound number 2. Compound number 3, we have these two hydrogens are exactly similar, so that here it is indicated as a triplet. And this hydrogen or the terminal 1 is having a doublet provision. So here triplet and doublet is indicated for this compound. That is given in the option number 1. Or that is given in the option number 1. So option number 2, doublet of doublet, correct. Doublet triplet is the wrong one. Doublet triplet is correct. So option 2 may not be correct. Option 1 is satisfying all the multiplicity patterns of 3 organic compounds in the proton NMR spectroscopy. So for question number 41, option number 1 will be the right answer. Let me go with question number 42. It is also related with the organic chemistry and pertaining with this molecular orbital theory. Among the following, the correct representation for least unoccupied molecular orbital represented as a LUMO of benzene is, LUMO of benzene is, right? So benzene molecular orbital diagram, if we are plotting, then you can clearly understand where you can find a LUMO, where you can find homo orbitals. First of all, we need to go for that MOT diagram of benzene molecule. Benzene molecule 6 pi electron system, there is a provision for 6 orbitals over there. So being it is a pi electron system, here the orbitals are indicated as a pi 1, pi 2, pi 3, pi 4, pi 5 and pi 6 star. So here pi 1, pi 2, pi 3 are said to be bonding molecular orbitals. Pi 4, pi 5, pi 6 are anti-bonding molecular orbitals, right? So pi 1 molecular orbital is having no nodes, nodal planes at 0, where all the lobes are indicated towards the upside direction, where 2 electrons are located within. Pi 1 is having 2 electrons. Pi 2 is having 3 lobes are indicated upward, 3 lobes are indicated downward. So there is a proximity for 1 nodal plane. Right, so here 1 nodal plane is indicated for this psi 2, and the same manner psi 3 is also having 1 nodal plane in the horizontal dimension, right? Here are the 2 electrons, here are the 2 electrons. Psi 2 and psi 3 are called highest occupied molecular orbitals, said to be HOMO, right? Here is the psi 4. Psi 4 proximity for the 2 nodal planes. 2 nodal planes are possible whenever we are taking upward, downward, downward, upward, downward, downward. So here only corner side lobes are upward and in between lobes are downward, so that there is a provision for 2 nodal planes. And in either you can notice 1 horizontal, 1 vertical plane is there in the psi 5 star. So here, these 2 are said to be lowest unoccupied molecular orbitals where electrons are empty. Orbitals are empty. You can't find any electrons over there. That's the reason why psi 4 star, psi 5 star are said to be LUMO orbitals. And the completely topmost is called pi 6 star, where you can locate all the lobes alternatively, so that the provision for the nodal planes are 3. 3 nodal planes are possible over there, and all alternate arrangement you can notice. Our question is, in the benzene molecule, LUMO orbitals to be depicted. So from that entire molecular orbital diagram of the benzene ring, so here the provision for first molecule, if you consider, so first molecule if you consider downward, upward, 3 downward, 3 upward, so that only 1 provision of nodal plane, it is the HOMO orbital, not LUMO. So you can strike off A. Option A containing options you can cancel out. 1, 2 may not be correct. Go with B. There is a provision for one of the vertical plane. One of the vertical plane is possible, vertical node is possible. And here is the provision for this LUMO-orbital for this benzene molecule. And here also we have nodal plane. So there is a provision for the nodal plane here. So this is also possible as a LUMO of benzene ring. So here this is also possible. B, C. Here you can notice there is a provision for this site 4 star. So here this C, option C is looks like a pi 4 star, and option B looks like a pi 5 star. It will be, that is given in the option number B. So B, C are provided in the option number 3. For question number 42, option 3 will be the right answer. Let me go with the question number 43. Question number 43. The major products A and B formed in the following reaction. Again, it is a part of organic chemistry. I'm taking a bridgehead carbonatum norbornanol system, and it is added with methyl magnesium bromide Grignard reagent and followed by hydrolysis carried under acidified conditions. What could be the compound A we need to analyze? And in either compound, you can notice same kind of bridgehead compound, but instead of carbonyl, there is a olefinic double bond at the same carbonatum. And here is the reagent also changed. Instead of Grignard reagent, here 9-BBN. 9-BBN is added. So this is hydroboration process taken, and subsequently hydrogen peroxide in the presence of sodium hydroxide is the another reagent is added. So compound B will be generated. So what are the major products A and B to be analyzed, to be identified? Ultimately, A, B is equal to CH3OH may not be correct because we are using different reagent. That's the reason why same product may not be possible. So that A is equal to B, A is equal to B. Blindly you can strike off. Option 1, option 2 may not be correct. There is a provision for 3 and 4 only. Let me go with option 3. Option 3 is having this methyl art exoposition, and your axial position is having hydroxyl functionality. This is the compound A. In this reaction, methyl is coming in the equatorial position like this, and the compound is originated. And in hydroboration, subsequently treating with the hydrogen peroxide, there is a formation of CH2OH. In case of this, in case of compound B, there is a OH formation is required like this. Both are satisfied in the option number 4. So here question number 43, option 4 will be the right answer. Let me explain what is the reason behind these product formations. Right. So Grignard reagent is mean for RMGX, methyl magnesium bromide added. Methyl magnesium bromide always added from the least hindered side. Okay, already ketonic functionality is there. Toward that ketonic side, it is not moving, rather opposite direction it is coming. That is called exophase. Least hindered exophase addition taken over this carbonylic compound and subsequently hydrolyzed. So there is a formation of alcohol like this. So that here exoposition taken at equatorial, and this is the feasible addition reaction with the Grignard reagent. Later on, 9-BBN. So hydroboration and followed by oxidation. Hydroboration always least hindered side, always it is following anti-Markovnikov rule over there, and that having the provision. If you're observing these two carbonatoms, this is the carbon with the total entire complicated skeleton located on this bridgehead carbon only. But this carbon is terminal carbon is somewhat free. Being 9-BBN is the complex molecule, it always prefer to bind at the terminal carbon rather than the second carbon atom. That's the reason why here the attachment at the terminal carbon 9-BBN. Subsequently H2O2 if added, here the BBN replaced with this OH, and that OH is located on the terminal carbon atom only. That is given in the option number 4. So this will be the option 4 will be the right answer for that one. So if you observe methyl magnesium bromide is coming, methyl magnesium bromide is coming in the exo direction, and here 9-BBM is coming toward this terminal carbon atom, being it is bulkier one. So in order to avoid steric hindrance, there is kind of attachment taken, and the most stable compound formation taken over there. This is the way these two options are provided in the option number 4. For question number 43, option 4 will be the right answer. Move on to question number 44. According to Calculus equation, vicinal proton-proton coupling constant is minimum when the value of dihedral angle is. It is related with the physical chemistry question. Calculus equation to be known to you, then only we can answer this one. Proton-proton coupling constant, minimum value in the dihedral angle value with the minimum coupling constant to be depicted. For that purpose, we have the Calculus equation over there. 3JH is equal to A cos 2 pi plus B cos pi plus C is the formula for the Calculus equation. And here is the dihedral angle. Theta is indicated for the dihedral angle. The coupling is minimum when the dihedral angle is approximately 90 degrees. That is indicated on the graph. If you observe the graph, it is very clear to understand. The magnitude of these couplings are generally smallest when the torsion angle is closer to 90 degrees. Smallest value is indicated as 90 degrees. And largest angles like 0 or 180 if present largest angle, that is giving the maximum value. So here the question is, minimum value is required. So 90 degrees is a minimum value. Maximum value is possible 0 degrees and 180 degrees as well. That is very clear. 0 degrees if present larger the value will be there. 60 degrees intermediate value will be there. 90 degrees very minimum value, that is only requisite coupling constant value for us. And 180 degrees anti and the maximum value again. So the dihedral angle if 90 degrees, so the coupling constant value will be minimum is the correct answer. So if you observe clearly, if this dihedral angle plotted again is this coupling constant value, here you can observe the deep valley. The deep valley here it is observed at 90 degrees and it is reaching the highest peak at the value of 180 degrees of dihedral angle. From this only you can clearly understand that it is applicable to the simplest molecule like ethane. Dihedral angle in the sense that adjacent to carbon atoms, the in between the angle to be taken into the consideration. So if the theta value is 90 degrees, so that minimum coupling constant value is observed. For question number 44, option number 3 will be the correct answer. Let me move on to question number 45. Again, it is the part of organic chemistry. The reagent that would affect the following transformation is, right? I'm taking a longer chain. So here is the nitrogen atom, that is tertiary. Upon the nitrogen 1 H, you can notice Bock. In either side, we have a CH2 OAC. And this is the carbon with the long tail of the carbon chain with the OTBS. And here is the side chain once again, that is the ethyl over the position number 1. So these many functionalities are located. If the same compound is converted into any other compound by the reaction with the suitable reagent, after the reaction, the probable product will be, there is no change in OAC. OAC remains as such. OTBS also remains as such. Only the difference is nitrogen Bock will be replaced with hydrogen. So that this is the question taken from the protecting groups. Specifically, some reagents are more specific for the removal of certain kind of reagents, certain kinds of capping agents. So here the specific reagent required to remove this Bock functionality over this nitrogen atom to be identified from the 4 options provided over there. First of all, we need to understand the concept of behind this protecting groups. Organic synthesis protecting groups are very essential because, for example, the compound was taken as such and added with the reagent. If reagent is added over that compound, what happens? The compound different functional groups, if existing, all are having equal proximity to react with that reagent and multiple products we will get instead of expected one. Instead, if you are protecting all the requisite functionalities and whatever reacting group is there, that only active toward the reagent added, so that expected product formation taking place. Later on, you can deprotect the capped functionality so that the requisite product formation is possible. This is the purpose of protecting groups. So organic synthesis always proceeded with this masking the functionalities which are not required to be reacted. So after reacting the expected functionality, we need to go for the protection of those functionalities which were already masked. So this is the way protecting groups are working. So in order to avoid the interference with the reagent and giving the multiple products instead of expected product. If tertiary butoxy-carbonyl group is there, tertiary butoxy-carbonyl is simply indicated as a BOC. BOC group is common protecting group for the primary and secondary amines as well, and typically stable to bases, nucleophiles, and hydrogenation may not affect that one. In order to remove this BOC reagent, the specific reagents like acids like hydrofluoric acid, tetrafluoroacetic acid, Lewis acid like aluminum trichloride, boron tribromide, such reagents, acidic reagents are very susceptible for the removal of BOC. So here the requisite removal of BOC only. That's the reason why our focus must be on AlCl3, being it is a Lewis acid, right? So that AlCl3 and solvent dichloromethane are suitable for this removal, and you will get this kind of deep protection. I hope this option 3. Let me go with another as well. Tertiary butyl dimethylsilyl functionality, OTBS. Tertiary butyl dimethylsilyl functionality if present. So here typically removed by the TBAF and HF pyridine, such reagents if present within the molecule, it will be removed. Okay. Acetate functionality is selective for the removal by the potassium carbonate and methanol. Such bases are selective for the removal of OAC functionality. So here the options whichever provided, hydrogen, palladium, carbon, and ethyl acetate, if considered, that is more selective for the removal of the CBZ functionalities. Benzyl type functionality, if present within the molecule, that will be removed. CBZ may not be present in the compound, so you can strike up this hydrogen, palladium, carbon. We are not focusing on CBZ deprotection. TBAF is tetrabutyl ammonium fluoride. This is more specific for the removal of OTBS. But here, after getting the product also, OTBS is preserved. It is retained, restored. That's why we are not supposed to use TBAF, THF, so that it will remove the OTBS functionality. That is also striked up. And go with the option number 3. Aluminum trichloride and dichloromethane. So AlCl3 is the stronger Lewis acid. It is more specific for the BOC. So that it will use to remove this BOC functionality. That is only the correct answer. Option 3 is the correct answer. The usage of potassium carbonate and methanol is a base, more specific for the removal of OAC. But within the compound, if you observe OAC, after the reaction also we got OAC once again. So you need not to use potassium carbonate. Only the provision to use is AlCl3CH2Cl2. For question number 45, option 3 will be the correct answer to deprotect BOC. Let me go with the question number 46. Again, it is a part of organic chemistry. IUPAC nomenclature based question. IUPAC stands for International Union for Pure and Applied Chemistry. The correct IUPAC name for the following compound is required to be answered. Here is the 6-member ring system with the double bond. Here is the methyl functionality. Here is the another 3-member ring. We can designate the compound as a bicyclic ring system. And here is the geminal dimethyl functionalities. Okay, if this is the case, bicyclic ring system was taken, certain rules to be followed in order to give the numbering for the system. If bicyclic ring system was taken into the consideration, numbering starts from bridgehead carbon always. This is the fundamental thing we need to follow. Whatever the carbons are there, we need not to consider wherever the bridgehead carbon means the carbon which is binding to, which is connected with the 2-ring system, that is called a bridgehead carbon atoms. So here that bridgehead carbon, from that bridgehead carbon also numbering should be started. So I'm going to start the numbering from this carbon atom. 1, 2, 3, 4, 5, 6, and this is the 7th carbon as well. So this is the way numbering will be given for the system. After getting the numbering for that one, here being the compound is given for the absolute configuration as well. So that let me go for first of all, Let me count the number of methyl groups where they are located. At the position number 3, we have a methyl. At the position number 7, 7 dimethyl are located. Let me indicate 3, 7, 7 trimethyl. So this is a kind of a substitution for view. And even at the position number 3, we have a double bond. So 3-ene is also present. And another thing we need to represent within the cyclic system, within the bicyclic system, one side you can notice 1, 2, 3, 4 carbon atoms. This side we have 4 carbon atoms, and this side we have 1 carbon atom. In between we have no carbon atom. So that 4, 1, 0. 4, 1, 0. 4, 1, 0 is indicated for all the bicyclic systems. So this kind of answering may not give the correct answer. 4, 1, 0 is given for all the options. 3-ene, 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 3-ene. All 4 options is indicated the position of double bond at third carbon only. That is also not possible to identify. And being it is a 7 carbon chain, 7 carbon ring system, hept is also same. So here from this data we are not supposed to identify. Only the thing is the position of methyl groups. Let me sort out position of double bonds. Position of methyl group. Methyl is there at position number 3 and position number 7 as well. 3, 7, 7. 3, 7, 7. Both are provided in the option 1 and 2. So option 3, 4, you can simply strike off, being 477, 477, wrong representation. And in order to get the exact answer, absolute configuration must be known. Absolute configuration determination is possible by using Koning-Predlog rules. And here is the carbon. First of all, I'm taking the carbon number 1, rich head carbon taken into the consideration. Around that carbon atom, we have to go for the numbering system. Here the first weight carbon is provided in the left hand side. Number 1 is provided in the adjacent carbon, number 2, and this is the number 3. Hydrogen least priority 4. If you are moving from higher priority, lower priority in this dimension, it is the anti-clockwise rotation. That's the reason why obviously C1 carbon is accompanied by the S absolute configuration. Let me go with this in either carbon atom at the position number 6. Position number 6 carbon atom, here the highest weightage carbon is located and the next weightage carbon is this side. And here is the third weight carbon atom is there and the least hydrogen is located away from the viewer at the 4th number. If you are moving from the highest priority to lowest priority in this dimension, clockwise rotation taken place. Clockwise rotation means for the R configuration that is taken at the position number 6. So here right representation will be first carbon S configuration, sixth carbon R configuration, 3, 7, 7, trimethyl, bicyclo, 4, 1, 0, hept, 3-ene. All are satisfied at the option number 1. For question number 46, option 1 will be the right answer. Let me go with the question number 47. The isopentenyl pyrophosphate formed through the mevalonate pathway using acetyl coenzyme A containing C14 labeled carbonyl carbon is. Right. So isopentenyl pyrophosphate formed through the mevalonic acid pathway. So if you know the natural product synthesis, then only it is possible to identify C14 labeled star carbon atoms where they are located to be identified. For that purpose, first of all, we have to know what is the mevalonic acid pathway for this IPP synthesis. Acetyl coenzyme A could be taken as a starting material, being they mentioned at this question only. C13 labeled carbonyl carbon, C14 labeled carbonyl carbon to be taken. C14 labeled carbonyl carbon, if taken, this will be the starting material and added with 1 mole molecule of the same one. Acyl coenzyme A will be added, so the dimerization taken like this, and the position of labeled carbons are indicated in this manner. Let me add one more same kind of molecule to this this one, and there is a trimer formation taken place. This is the kind of trimer. And here is the reduction taken place. The reduction is accomplished over there. Whenever reduction is taken upon this molecule, acetate remains as this, CH2 remains as this, CH3OH remains, and here is the CH2. Here is the C double bond wo S COA totally reduced into CH2OH. This is the kind of reduction process in the presence of NADPH H plus. The formed molecule is called mevalonate. Formed one is called mevalonate, and there is a labeled carbon atoms you can clearly observe. After getting this kind of molecule, that is supposed to go for the decarboxylation. This terminal is having carboxylate functionality to be decarboxylated. Whenever decarboxylation taking place, there is a provision for the generation of double bond. Double bond molecule with the CH2OPP, which is called isopentenyl pyrophosphate. This is IPP. If you count the number of carbons in the IPP, position number 2, and position number 4 are having C14 leveled carbon atoms within the molecule. So initially that is there at the carbonylic carbon only. That is supposed to be go with the mevalonic acid pathway for the synthesis of IPP. After getting this IPP, you can notice the labeled carbon atoms are the second and fourth positions within the molecule. So second and fourth positions are mentioned. Second and fourth positions are mentioned at the option number 3 only. C2 and C4 positions are mentioned option number 3 only. That option number 3 will be the right answer for question number 47. If you understand this entire way of mechanism, then only it is possible to identify the position of labeled carbon atoms. Let me repeat one more time. Acyl coenzyme A is supposed to be binded with either acyl coenzyme A dimerization, followed by trimerization, followed by reduction, followed by decarboxylation, giving rise to IPP, where labeled carbons are located at second and fourth carbon atom. That is given in the option number 3. Move on to question number 48. It is a part of physical chemistry. The wave function psi x of one-dimensional quantum system is given by psi x is equal to ax experimental minus x squared by a squared. The dimension of A is L is the dimension of length. L is designated as the length dimension. If that is the case, then dimension of A to be identified from these 4 options, right? So here normalization and dimensionality of one-dimensional wave function is indicated as the wave function one-dimensional box must satisfy normalization condition. Integration psi x squared dx is equal to 1. Psi x squared must have the dimensions of 1 by length. 1 by length nothing but L inverse. Length dimension is L. L inverse can be taken being it is a denominator. This is the dimension for psi x squared, but we have psi x only. If you are removing square, there's L inverse now converted into L to the power minus 1 by 2. L to the power minus 1 by 2 is the dimensions of psi x. So here is the term you got it for psi x. Psi x is equal to A into experimental minus x squared by a squared, right? So here experimental minus x squared by a squared is the dimensionless quantity, being x squared a squared is the dimensionless quantity. So here A is equal to x is equal to length. That is the dimension for the concentration of A and concentration of x as well. Psi x value is known to you. That is length to the power minus 1 by 2. Psi x is equal to, the formula is known to you, A into x into experimental minus x squared by a squared. Psi x is equal to A into x into the entire experimental minus x squared by a squared is the dimensionless, right? Simply you can indicate as the dimensionless quantity. That indicates what? Psi x is equal to A into x is equal to psi x value is length to the power minus 1 by 2. Then x is equal to length, right? X is equal to length. So x is equal to length, that is A is equal to length to the power minus 3 by 2. A is equal to length to the power minus 3 by 2. That is given in the option number 3. So question number 48, option 3 will be the correct answer. Let me go for Question number 49. Again, it is a part of physical chemistry. For an eigenstate psi of time-independent Hamiltonian, the eigenstatus psi to be identified. For that purpose, if the system is in the eigenstate of the time-independent Hamiltonian, the time-dependent wave function is given by psi xt is equal to psi x. Here t value is e to the power minus I e t by h cut, right? So here psi x is a time-independent spatial part, and e to the power minus I e t by h cut is time-dependent phase factor. So both are different. Time-independent is psi x. Time-dependent is this negative fraction, right? Here is the formula for the probability density. Probability density P is equal to psi x comma t whole square. The is equal to, so here psi star xt psi xt. Here psi square is nothing but psi star into psi, right? Here psi star xt into psi xt is the probability density. Substituting the values over there, right? So if you are substituting these values over there, here psi xt value is known to you, that is P is equal to psi x, the t value is e to the power I e t by h cut dot psi x e to the power minus I e t by h cut. Because here we have a negative sign and positive sign, that's the reason why negative get cancelled. So here a positive will be there, and here negative sign remains as such. So if you are taking this these two, the multiplication of these two, negative fraction and positive fraction got cancelled out, and here psi x into psi x will become psi x square. The value will become psi x square. So the probability density is time independent. There is no time factor within this. Probability density is a time independent factor because time factor is not represented within. So although wave function psi xt has a time dependent exponential factor, this is cancelled. So if you are taking psi square, the factor time dependent fraction got cancelled out. The wave function psi time dependent exponential term e to the power minus I e t by h cut. However, probability density is time independent. One is dependent, another is independent. Here, wave function is a dependent fraction. Probability density is an independent fraction, right? So here psi is the time dependent, but psi star psi is the time independent factor. That is given in option number 2. Psi is time dependent, and psi star psi is time independent fraction. It will be, that is given in the option number 2. For question number 49, option number 2 will be the correct answer. Option number 2 will be the correct answer. Again, it is a part of another question. Question number 50 is the part of physical chemistry. Once again, among the following linear combinations of determinants written with the spatial wave functions 1s and 2s, electronic spin wave functions alpha and beta, 1 and 2 labels of the two electrons, one that denotes unnormalized wave function triplet excited state 1s1 2s1 of helium is. So it's a purely physical chemistry based question, and triplet excited state 1s1 2s1 of helium to be taken, unnormalized wave function to be identified from this data. Electrons are Fermi ions. The total wave function must be antisymmetric under the exchange of two electrons. If you are exchanging two electrons, your antisymmetric geometry is allocated for that one. Total wave function is equal to spatial part into spin part. So spatial part is multiplied with the spin part, then total wave function is calculated. If the spatial wave function is symmetric, spin wave function must be antisymmetric and vice versa. In order to make the total wave function, one must be symmetric, another must be antisymmetric. Triplet state is taken, S is equal to 1, spin overall spin is equal to 1, have symmetric spin wave function. So spatial spin part must be antisymmetric, it will be. If you are taking triplet state of the helium 1s1 and 2s1, helium excited state 1 electron in 1s orbital and another electron in 2s orbital. Two wave functions is equal to spatial part into spin part. Fermi ion, that's why antisymmetric must be present during the exchange of electrons. Replace state always S is equal to 1. Spin wave function is symmetric. That is alpha 1 beta 2 plus beta 1 alpha 2 alpha alpha beta beta. Therefore, spatial wave function must be antisymmetric. So always there is a opposition between these two, spin and spatial. At the condition, 1 is alpha 1, 2 is beta 1. 1 is alpha 2, 2 is beta 2 minus 2 is alpha 1, 1 is beta 1, 2 is alpha 2, 1 is beta 2 is the correct representation. Spatial part, 1 is the alpha 1, 2 is beta 2 minus 2 is alpha 1, 1 is beta 2 is the right representation, being it is antisymmetric. It's written as a linear combination of determinants showing antisymmetry under exchange. Exchange of 1 and 2 sign changes, antisymmetric spatial part is possible when it is a triplet. So option 2 is the correct representation that is provided like this. 1 is alpha 1, 2 is beta 1, 1 is alpha 2, 2 is beta 2 minus 2 is alpha 1, 1 is beta 1, 2 is alpha 2, 1 is beta 2. That is represented in the option number 2. For question number 50, option 2 will be the right representation. Move on to question number 51. For a diatomic molecule AB, internuclear distance is indicated as R and the internuclear axis is taken in the Z direction. The plot of overlap integral is for the px orbital A and dzx orbital of B against R is. So if you observe the entire graphs, so S versus R were plotted. Here the overlap integral is taken as S and R is the internuclear distance. Overlap integral if started at this point, that is non-zero. So that is a 0 is taken over there. So here if it is taken, the curve is starting from this, that is non-zero. In the option number 2 is also S value. S value is overlap integral is non-zero. In the option 3, overlap integral value is 0 and here R value is also 0 at the end. Here the option number 4, we have overlap integral value non-zero and R value is becoming 0 at the end. So these many 4 curvatures are provided for this diatomic molecule AB. You need to identify what is the correct answer. The overlap integral quantifies the extent to which atomic orbitals are overlapping. That is indicated with S. S is equal to integration chi A star chi B d tau. Magnitude of S overlap integral is crucial for the determination of strength of the chemical bond. Greater the S value, stronger the overlap taking place. Bond is very stronger in nature. Dependence on the internuclear distance. If R is equal to 0, hypothetically, nuclei are superimposed. R is equal to 0 is nothing but 2 nucleus are closer to each other. At that condition, 2 orbitals are identical and overlap integral S is equal to 1. However, orbitals are different parity or impossible symmetry, incompatible symmetry, so that overlap may become 0 as well. 2 possibilities we have at this R is equal to 0 condition. If R is equal to infinity, means 2 atoms are far apart, infinity distance is there in between, so that overlap is becoming 0 and S value obviously becomes 0. At some intermediate distance, overlap integral reaches the maximum value. Overlap integral reaches the maximum value and there is a greater extent of overlap taking between the 2 orbitals and giving higher the S value. Orbital symmetry, the orbitals involved p orbitals. Assume pz of sigma bonding along the z axis taken and dz orbital of b was also taken over there. Pz and dz square have the appropriate symmetry for forming sigma bond in between along the z direction. If that is the case, R is equal to infinity, then S value will become 0. R is equal to 0, again S value will become 0. R is equal to intermediate distance at the condition the value will be maximum. All these are provided. All these are provided by the graph number 3 only, because when R is equal to 0, the S value also becomes 0. When r is equal to infinity, the s value will become 0. When r is equal to some intermediate distance, higher s value you can obtain, that is given in the option number 3. So for question number 52, option 3 will be the correct answer. Let me go with the 53 question. Considering the potential energy at the equilibrium position to be 0, the internuclear potential Vx as a function of the distance x between the two atoms, the atomic molecule is given by Vx is equal to dE 1 minus e to the power minus alpha x minus xe whole to the power 2. Where dE and alpha are two constants, the force constant of the bond between the two atoms is indicated. So if 4 are the options, then what will be the force constant value we need to identify? For that purpose, force constant from the potential energy function, the force constant is indicated as K. The atomic molecule represents stiffness of the bond and calculated as the second derivative. Mathematically, force constant K is equal to d square V by dx square at x is equal to xe. Then Vx if taken, Vx formula is provided within the problem. Vx is equal to dE into 1 minus e to the power minus alpha x minus xe whole to the power 2. So this is called a Morse potential, right? So here the potential y is equal to x minus xe. Then Vy is equal to dE into 1 minus e to the power minus ay whole square. First derivative of this one, dv by dy is equal to 2 dE alpha e to the power minus xy 1 minus e to the power minus alpha y. This is the first derivative. Second derivative, d square v by dy square is equal to 2 dE alpha into minus alpha e to the power minus alpha y plus 2 alpha e to the power minus 2 alpha y. This is the second derivative for the equation. At the equilibrium, y value will become totally 0. At that condition, e to the power minus alpha y is equal to 1. So if you are going to substitute this value in the above equation, d square v by dy square, d square v by dy square, that is second derivative, become is equal to 2 dE alpha into minus alpha plus 2 alpha is equal to minus alpha plus 2 alpha. If you are taking the entire calculation of this one, 2 dE alpha square is the correct answer. 2 dE alpha square is the force constant value that is provided in the option number 2. That is provided in the option number 2. For question number 53, option number 2 will be the right answer. So this is calculated by taking Morse potential equation, and its second derivative is considered, where equilibrium y will become 0, so that e to the power minus alpha y become 1. If you simplify the equation of the second derivative, that will become 2 dE alpha square. That is the force constant value provided in the option number 2. For question number 53, option number 2 will be the right answer. By this, we successfully completed the entire session. Hopefully, you got the detailed information regarding the CSIR NET previous year question paper and how can we solve if the questions are provided from the various regions of chemistry. And most probably, this kind of session is helpful for your deep preparation towards government examination sector and state eligibility for teaching, national eligibility for teaching, and JRF fellowship as well. So this kind of session is most helpful. Follow the channel and watch regularly and share with your friends so that we will get the detailed explanation, and daily content will be added over there. So you will get definitely get the success in your field. Thank you very much. Signing off, Dr. Kavitha Kuttireddy.